Hello, I'm Dan, and this is Dan Explains. Recently I did a video on the definition of a planet, so I thought I'd do another video about objects in space you'd assume you understood were clearly defined. Today I'm explaining what a star is, or what objects people debate are stars or not. Conveniently, one side of the planet debate I didn't go over is what's too big to be a planet, or when does a planet stop being a planet and become a star. No, the kind of star you see in the sky, and without using a catapult. What's the smallest a star can be, and what's the biggest it can be? Let me explain. All of you probably learned in grade school that the sun, and all the stars for that matter, are giant balls of burning hydrogen. Of course, the hydrogen isn't burning in the same sense as it would be on Earth. The intense pressures inside the star cause the hydrogen to fuse with more hydrogen, releasing energy in a similar way to the hydrogen bomb. That's pretty much the de facto definition of a star. That is, that the object has enough gravity to be capable of hydrogen-hydrogen fusion. Although it's not so simple. Let's first consider supermassive objects. Is there a limit to how big a star can be? I mean, when a star gets too big, it becomes a black hole, right? Well, not exactly. In reality, it seems there are no upper limit to a star's size. What limits a star's size in the universe today is the amount of material available when the star is forming. The more massive a star is, the faster it burns through its fuel. Counterintuitively, even though large stars have way more fuel, they burn through it so much faster than the small stars, they have shorter lifespans, making massive stars much more rare than small stars. Not only because they have to acquire much more mass, but because their lifespans are on the order of millions of years, not billions. It's only after a star's death that the objects like black holes, neutron stars, and white dwarfs form. We don't call black holes stars because, well, they're black. We do call neutron stars and white dwarf stars, but they aren't in the same sense as our sun. Eventually they will all cool and not shine like stars anymore, since their light comes from latent heat. Ignoring the occasional nova anyway. You know, kind of like the hot potato you just pulled out of the oven. All three are more or less corpses of stars, but they aren't really stars. I mean, what would happen if you had a planet made of pure iron and just kept adding iron and heavier elements? It would never become a star. It would directly collapse into a neutron star at some point, with no star-like stage. Well, what about the lower limit? As you probably also learned in grade school, the gas planets are big planets made mostly of hydrogen, but they're not large enough to fuse hydrogen. The cutoff for the planet becoming a star is between 40 and 80 times the mass of the planet Jupiter. A pretty broad range, I know. This is one reason why a star is so hard to define. You see, most of what we call main sequence stars, like our sun, burn pretty much just hydrogen. However, every atomic nuclei lighter than iron releases energy when it undergoes fusion. Iron and all nuclei heavier need energy added to achieve fusion. The energy of the nuclei in the periodic table of elements creates sort of a funnel shape, with iron at the bottom. So under the right conditions, everything, that is, all elements, want to be iron. Hence why we find so much iron in the environment. Anyway, once stars start to run out of hydrogen, they start to burn heavier and heavier elements, slowly building up iron in their cores, until they reach a tipping point, where there is no longer enough burning matter to hold the gravity of the rest of the matter back. So yeah, the point is stars burn a lot more elements than just hydrogen and are still considered stars. So, sustained fusion must be the dividing line between planets and stars, right? I mean, after all, there's no elements lighter than hydrogen. Well, that's not so simple, of course. You see, the heavier the nuclei is, the more protons it has, which repulse each other, making the fusion harder. This is why heavier elements burn later in the star's life. However, there are neutrons in the nucleus too. These don't repulse each other. They increase the nucleus cross-section, increasing the likelihood of fusion. In this tug of war between protons and neutrons, the protons always win as the elements get heavier. But most elements have different isotopes, which are nuclei with the same number of protons, but a different number of neutrons. Hydrogen just happens to have 3 isotopes: the regular single proton isotope that we're all familiar with, and its other isotopes which were lucky enough to get their own names, and they are deuterium, with 1 proton and 1 neutron, and tritium, which has 1 proton and 2 neutrons. Both fuse much more easily than simple hydrogen. Tritium is radioactive, so you don't find it in enough abundance for the stars to be made out of it. Deuterium is stable, however. So, it's deuterium that really blurs the line between planets and stars. Astronomers made a new class of objects to hold these deuterium-burning bodies called brown dwarfs. The name dwarf implies that they are small brown stars. Some astronomers do consider them stars. In fact, if you look on Wikipedia, yeah, I know, not exactly a reliable source, they are on the list for small star types. Other astronomers consider them to be their own thing altogether. Even when the IAU set the definition of a planet in 2006, they didn't go anywhere near what the upper limit of a planet could be. If you ask me, which you might be curious about my opinion since you're watching this video, if the object is heavy enough to burn any isotope and does, it's a star. That being said, what a star is and is not will probably be debated for some time yet, since we have no borderline analogs in our solar system in desperate need of a definition, unlike planets. Poor Pluto. Thank you for watching. If you like this video, please press the like button, subscribe to my channel, and ding the bell to get notified when I post new videos. Also, please support me on Patreon, link in the description. The more people support me, the more time I can dedicate to making videos like this one. So, until next time, have a great week.